Hello everyone. In this video, we review Kirchhoff's circuit laws, namely KCL and KVL. We also review how to convert a KCL equation and represent it in terms of node voltage. Same for KVL, we represent it in terms of mesh current. This leads us to node voltage analysis and mesh current analysis. Both are simple yet effective techniques to solve for circuit parameters. We start with the current law, KCL. The Kirchhoff's current law states that the summation of all current entering a node must equal to 0, or in other words, summation of current entering the node should equal to summation of the current leaving that node, and this comes from the principle of charge preservation. No charge is being stuck or stored into a node. So a node is just a pathway for the charge to go and split if we have more than one branch. In general, with a circuit that has n nodes, we can write n-1 independent node equation. So let's practice that on this given circuit here. So here I have a circuit with 4 resistors. Each resistor has an associated current I1 through I4, and you can easily identify that we have 3 nodes, node A, node B, and down here we have node C. So with 3 nodes we can write 2 independent KCL, so we only need to write KCL at 2 different nodes. So let's pick node A and node B. So I'm going to write a KCL at node A, and we'll do the same for node B. So those would be the 2 independent equations that I can get from this circuit. So if you look at node A, we have current I1 is entering that node. Nothing else is entering, so I'm ready to write an equal. And then I have I2 is leaving. So this would be the first Kirchhoff equation that we can obtain using node A. Now we are ready to move to node B. If you look at node B, I have I2 is entering, I4 is also entering, but I3 is leaving. So the law states that summation of current N should equal to summation of current out. So I have I2 and I4 is going in, and I have I3 is going out. Now if you look at the circuit, we have 4 current unknowns. Yet, we only have 2 equations. Therefore, we need to come up with either 2 more equations or find a smarter way to solve for those 4 unknowns using these 2 equations. Okay? One can suggest, okay, like, how about we use Ohm's law? So if I use Ohm's law, I can represent each current of these as a voltage over a resistor. So I1 would be the voltage V1 divided over resistor R1. This is using Ohm's law. Same for I2. I2 is the current going through R2, so I can write it as V2 over R2. I can do the same with the second KCL at B. I have I2. I can replace I2 as V2 over R2 plus I4. I4 can be written as V4 over R4. And finally, I3 is equal to V3 over R3. However, after using Ohm's law here, I replace the current, still replaced it with 4 unknown voltages. I cannot solve for those 4 unknowns using only 2 equations. So, the node voltage analysis came up with a nice trick. He said, okay, instead of using the actual voltage, how about we use the node voltage? So for any device that we have here, assume this device here across which I have a voltage V1. This V1 is connected between 2 nodes. So how about I define a node voltage, where when we define a node voltage, it would be taken relative to some reference point, we call it ground, where the voltage at the ground is 0 volt. And as a result, if I have an actual element whose actual voltage here, V1, I can write V1 as the difference between the 2 node voltages connecting this element to the rest of the circuit. So for this element down here, I have the first arm, or the first node, is VA minus VB. So I replace the actual voltage as a superposition or a difference between the potential or the voltage at the two nodes connected to this element. Okay, so now let's apply this voltage analysis technique to our circuits that we have. Okay, so now I have V1. As V1 is on this element R1, I can write down that V1 as, okay, so I have two nodes here that are connected to R1, across which we have V1. So the plus sign is relative to this node C, so V1 can be written as the difference between two node voltage. First node is C, VC, minus the node corresponding to the negative terminal is A, it's VA. Okay, we can do the same for V2. So V2 has two nodes, is between two nodes, is node A and node B. The plus is associated with A, the minus is associated with B, so it's equal to VA minus VB. If you look at V3, R3 is between two nodes, node B and node C, so V3 can be written as VB minus VC. And finally, V4 is connected between the same two nodes, B and C. But now, the plus is associated with node C, so this is VC, minus the minus is associated with node B, so VB. Okay? Now, those three node voltages are relative to one reference point. So now we have to manually pick a reference. It could be any node that is being a reference. Okay? So for simplicity, let's assign node C to be a reference, and if we did so, I now announce that VC is equal to 0 volt. Okay, so all voltage will be measured with respect to node C. Okay, so now I can update my expression for V1. It would be 0 minus VA equals to VA. Expression for V2 still the same, it's VA minus VB. For V3, it is VB minus 0, this gives me VB, and for V4 it is equal to 0, minus VB equals to minus VB. Now, what is nice about that is that even though I have 4 different voltages, I could represent them using only 2 parameters, VA and VB. Okay, so if I take this representation, use it into what we have currently for the KCL equation. So for V1 I have equal to minus VA over R1 equals V2 is equal to VA minus VB over R2. Okay, let me do the same for the KCL at node B. I write it in terms of V2, V3, V4. Let me replace V2, 3, and 4 in terms of the node voltages. So V2 is equal to VA minus VB plus V4 over R4. V4 is equal to minus VB. And finally, V3 over R3, I can represent V3 as VB according to our analysis on the right here. Now, I have 2 equations, equation 1 and equation 2, still 2 KCL equations, but now these 2 KCLs are represented in terms of node voltages. What is nice now is that I have 2 equations associated with 2 unknowns, VA and VB. So now I can solve equation 1 and equation 2 simultaneously, and this is called node voltage analysis. Once I have solution for VA and VB, I can immediately go and solve for V1, 2, 3, and 4, and also can solve for the corresponding current I1 through I4. So this is formally known as the node voltage analysis technique. The second Kirchhoff circuit law that we have is the voltage law. The voltage law is about the voltage within each loop. The law states that the voltage drop across all elements in a loop must add up to 0. if I have a circuit with n loops, I can write n independent loop equations. So let's apply that to this example here. So if you look here, I have two loops. So this is loop number 1, and this is loop number 2. I can write KVL in each loop, and this will give me two independent equations. So let me write a KVL in loop 1. When I go over the elements in loop 1 clockwise, so I start from the far left, I have plus V1, plus V2, and then plus V3, and this completes the loop. So summation of V1 plus V2 plus V3 equals to 0. And this is the KVL equation for loop number 1. I can do the same for loop 2. So KVL in loop 2. So in loop 2, I have only two elements. So if I go from the far left corner, I start from here. So I have minus V3 and then minus V4, and this completes the loop. So I have minus V3 minus V4 equals to 0. Now I have two equations, but how many unknowns? I have 4 unknown voltages. So it is the same issue as the KCL. The number of unknowns is larger than the number of equations. So we either need more equations or come up with a more innovative way. Okay? So one suggestion is, okay, let's use Ohm's law. I can represent the voltage as a current times a resistor. So V1 is equal to R1 times I1. V2 is equal to R2 times I2. And V3 is equal to R3 times I3. I just use Ohm's law to represent the voltage as resistance times the corresponding current. I can do the same for the bottom equation. First of all, I can multiply this equation by minus 1, so I get V3 plus V4 equal to 0. V3 is equal to R3 I3, and V4 is equal to R4 I4. So now I converted the voltage into a current time resistor, but we still have the same issue. I have two equations, but how many unknowns? Still 4. I1 through I4. So here kicks in the technique, which is the mesh current. So we introduce a mesh current where we define a current for each loop that we have. So I define a current Ix for this first loop, and I define a current Iy for the second loop. Then the actual current in element number k would be a superposition between these two loop currents. Okay? If an element is shared between two loops, like element R3 here, I can write that I3 is equal to a superposition between Ix and Iy. So should it be Ix minus Iy, or should it be Iy minus Ix? This actually depends on the directionality. So if you note here, you can see Ix is pointing down when it visits R3. So it matches the same direction as I3, so Ix take a positive. And when you look at Iy is actually pointing up when it visits R3. And this mismatch the direction for I3. And that's why we have a negative sign here. Okay? Now, all other elements live in only one loop. There is no shared loop for R1 or R2 or R4. So R1 here only lives in loop 1. So the actual current I1 would be equal to the loop current Ix, plus or minus depend on the directionality. So now when you look at Ix, when Ix is visiting R1, it points up in the same direction as I1. So I1 is equal to plus Ix. Okay? Same. When Ix here is visiting or traversing R2, it follows the same direction as I2. So I2 is equal to Ix. Note here in R1 and R2, the only loop current components that loop through them is Ix, and as a result I have only here Ix. Whereas R3 is shared between two loops, so it has Ix looping from left and it has Iy looping from right, and that's why we have I3 written as a superposition between Ix and Iy. Okay. The final current that we didn't cover yet is I4. I4 is the current through R4. Now when you look at the loop current, looping resistor 4 is only Iy. So when Iy is going into R4, it's going from top bottom, whereas I4 is going bottom up, so there is a mismatch in directionality. To correct for this mismatch, we have a negative sign, so it's negative Iy. So now what I did is I represented the 4 different currents that I have in terms of only 2 mesh currents. And now if you go back to our KVL equations, if I replace each of those currents in terms of the corresponding loop currents, I'm going to have simplified equation in terms of only 2 unknowns, which are the loop currents Ix and Iy. So let's do it together. So I'm going to use this equation that has the resistor times the current. I have R1 times I1 is equal to Ix, and then plus R2. I2 from the previous slide is equal to Ix, plus R3, I3. Now I3 is an shared element between the 2 loops, so I3 would equal to superposition between Ix and Iy. Ix matches the same direction as I3, so it takes a positive sign. Iy mismatch the direction of I3, so it takes a negative sign. And this completes this equation. Now a bit of algebra. Combine what belong to Ix together and what belong to Iy together. So I have R1 plus R2 plus R3 times Ix minus R3 Iy equals to 0. Let me call this equation number 1 and stop here. Now let me move to the KVL into the second loop. So this is the KVL that I have in the second loop. Right now I have it represented in terms of I3 and I4. So how about I replace I3 and I4 and represent them in terms of the loop current. So the equation I have R3 I3. Now I3 is equal to Ix minus Iy, as we described in the previous slide. And finally, the last terms are I4, and I4 is equal to minus Iy. Okay, and the right hand side is equal to 0. Again, use algebra to simplify this equation. Whatever belongs to Ix is here. Okay, and then I have minus R3 plus R4 times Iy equals to 0. And let me call this equation 2. Still I have 2 equations because I still only wrote 2 KVLs. But now what is nice about these 2 equations, they are a function of only 2 unknowns, Ix and Iy. So once I solve for Ix and Iy using simultaneous solution of these 2 equations, I can solve for the corresponding I1, 2, 3, 4. And once I have I1, 2, 3, 4, I can solve for V1 through V4. So basically I have the voltage and the current everywhere once I have a solution for Ix and Iy. So this approach here is called mesh current analysis, where I start by writing a regular KVL and then replace the actual current via a loop current and then simultaneously solve for those loop currents. And once I have the loop current, I can get all actual currents, and as a result I can also get all actual voltages. So in conclusion, in this video we reviewed 2 basic circuit laws, KCL and KVL, but KCL and KVL alone are not sufficient because I may have the number of equations less than the number of unknowns. And here comes the trick in the node voltage analysis and the mesh current analysis. The trick is if you write a KCL, you replace the current as a voltage over a resistor, and then this actual voltage of an element can be represented as a difference between the voltage of the two nodes connected to that element. On the other hand, if you're using KVL, you write down summation of voltage equal to 0, then you replace this voltage as a resistance times a current. But this is an actual current. The trick here in mesh current analysis is that you replace the actual current and rewrite it in terms of the mesh current, which now would reduce the number of unknowns and help us to use this smaller number of equations to solve for either the node voltage or the mesh current. And from there, once you have either the node voltage or the mesh current, you can solve for the actual voltage and current in all circuit elements. Thank you so much.